Okay, so I started this discussion of equalization by looking at what is the best that we can do. Okay, I focus on intersymbol interference as the example of when we would need equalization, and then I talked about, this intersymbol interference, what does it create, and how can I undo it? Maximum likelihood sequence estimation. But this section is about equalizers, and there's actually a whole lot of different kinds of equalizers I can use. So now I'm going to go over a little bit of a taxonomy, step back, now that we know what the optimal is, and start looking at where else could I look for interesting solutions to equalization problems. So, one way I could divide the class of equalizers is into those which deal with sequences and those which make symbol-by-symbol decisions, which I also like to call a one-shot decision. One tested statistic that I sort of, not one statistic, that's inaccurate. Symbol by symbol means I don't have to look at a sequence. So sequence versus symbol by symbol. So in the sequence, we have the MLSE. That was the first thing I looked at. And I talked about some suboptimal ones, like truncate the impulse response, or I don't know the impulse response, but I'll estimate it, so it's not going to be completely optimal, but it'll be pretty good. So these are the ones that fall in the category of sequence. And we're going to see a couple examples of a symbol by symbol instead of a sequence approach, which is linear filtering, so just using a regular linear filter. And another one is a feedback mechanism, so I'll be talking about that more later. But anyway, sequence versus making the time comes, the output of my filter comes, and I make a decision. That's the symbol, and I don't look back and I don't look at a sequence. So in the category of symbol by symbol, I said there was linear filters and I said there was this feedback. Now I'll give you a couple names. The linear filter, we're going to look at two, and the first one is called a zero forcing equalizer, and I'll be talking about that at length. I'll just throw out right now one characteristic. The idea is you find the inverse of the frequency response of your channel and you apply that. Interesting, we'll talk about that later, but it's a filter. I apply a filter. And the filter has a frequency response which is the exact opposite of the frequency response of the channel. Sounds intuitive. Then I'm going to talk about minimum mean squared error equalizer. And this equalizer is focusing on the impact of the noise, which is not really mentioned in this one. So we'll be looking at both of these linear filters quite closely. And I said there's going to be a feedback one, and the only feedback equalizer I'll be talking about is the decision feedback equalizer. And that'll be the last thing we cover kind of quickly. So I talked about sequence versus symbol by symbol. Another way I could sort things out is by linear versus nonlinear. Very different approaches. In the linear, I said we're going to be looking at two, the zero forcing and the MMSE. And in the nonlinear, we already saw the MLSE, and we're going to also be looking at the decision feedback equalizer. I can also divide the kinds of equalizers into fixed versus adaptive. And really, which one I want to use, fixed or adaptive, depends on the channel. It all depends on the physical layer characteristics that I have to deal with my channel. If the channel is static, it just doesn't change much. It has a certain response, and that's the response today, tomorrow, the next day, every minute to minute, doesn't change. Then a fixed equalizer would be the best approach. Things aren't changing. I don't have to worry about it. But what happens with a dynamic channel? A dynamic channel, well, then I can't just estimate the channel once, design an equalizer and use it because the channel is changing. So that's not a good approach with a fixed equalizer. So the decision feedback equalizer is one way I can deal with a dynamic channel. And another version is to actually just make adaptive versions of the linear filters. So the linear equalizers. What I'm going to show you in the beginning is here's the channel, here's how I find the equalizer from that channel. But then I could just as easily say, I'm not going to calculate it from a known channel. I'm going to use a training sequence and find the coefficients, not exactly, but adaptively. And when I use that adaptation, there's a couple of different numerical approaches I can use for the adaptation. One of them is known as LMS, or least mean squares. The other one is RLS, or recursively squares. And these are just two numerical approaches to how I would do the adaptation. So I mention them. We're not going to cover them in the course. I mention them because you're going to read somewhere, and you're going to read, oh, it's a zero forcing filter with an RLS adaptation. You're going to think, what? I never saw that before. No, it's just using the approach of the equalizer that we'll be discussing, and then which ways am I going to implement it. So don't be put off by that. So, taxonomy. So now I have a nice figure that sort of puts all these ideas into some orderly presentation about how I could think about what's going on with the different kinds of equalizers. And the first division is between linear and nonlinear. So very different approaches, implementation complexity, very different. Generally, linears are much less complex to implement. Not always, but generally. In the linear, there's a couple structures that I could use and the kind of filters, a lattice filter, a transversal filter. And we're going to be focusing on these transversal filters. And here we have the two fixed methods and the adaptive methods of the same filters. And over here we have the MLSE under the nonlinear and the decision feedback equalizer. Now, this idea of equalization has like a dissenting opinion. So first we're going to talk all about these different equalizers that we could use, and then I'm going to say, but you know, sometimes it's better just to avoid the problem, to not try to fix the intersymbol interference, but instead try to avoid the intersymbol interference. Remember, we already had one strategy for avoiding intersymbol interference, and that was using the Nyquist pulses. Nyquist pulses are an attempt to keep the intersymbol interference controlled. Okay? But if I try to put it through a very, very narrow band channel, you know, if I can't make my signal fit in that channel, well then, you know, the Nyquist isn't going to work. Nyquist just can get me as small as I can, and if that's still not small enough, then that's not going to work, and instead I'm going to go look at equalization. But there is another strategy I could use. It's a frequency domain technique that lets me sort of avoid needing an equalizer. And that's called discrete multitone, DMT, which is kind of like a variation on orthogonal frequency division multiplexing. So I'm going to take the time to introduce what is OFDM as a first step, and then how do we use it for DMT? Why, with this approach, can we avoid equalization? And that'll sort of finish up the discussion of equalization. So it's sort of the anti-equalization. So it's a completely different strategy. No filtering, no MLSE. It's really a trick for avoiding equalization. So now I'll start talking about the linear equalizers. Now remember, intersymbol interference can come from different types of sources. And we've spent a whole lot of, I introduced the discussion of equalization with this approach, where I assume that the intersymbol interference came from this idea of putting a signal through a very narrow bandwidth. But that's not the only way that I can get intersymbol interference. There's many other ways that it can come about. Now let's talk about one of those ways is in optical fiber. And the transmission media of optical fiber, there are wavelengths which travel at different speeds in the fiber, and if I have a wide enough signal, part of those signal content will travel at rates different from other parts of that signal content, which if I was going to summarize it, I would say that the pulses are spread. This only happens if I try to send information really, really fast. If I'm not going very fast, that doesn't happen. But this is not the bandwidth of the channel like it is up here. It's not because I'm going fast that I don't have enough bandwidth. What happens in the optical fiber is I have plenty of bandwidth, lots of bandwidth. It's just that the signal is acting a little differently in one part of the frequency than in the other. It's kind of a tricky dispersion. So it's called chromatic dispersion. And another place that we see intersymbol interference occur, very, very common, is in a wireless channel. And in a wireless channel, we will have many reflections. So think of it. You have two antennas. That antenna is a little hard to see. Let's just put it over here. So we have two antennas. And of course there's something called line of sight, which means that this antenna, generally, we have an antenna that will go omnidirectional. I could have a directional antenna, but let's say I'm using a omnidirectional antenna or one that's pretty wide, which I would want to do if I wanted to have good coverage, like for cellular. I've got a lot of people walking around with cell phones and I can't just point at one of them, so I have to have an antenna that lets me see all of my clients. But what happens is, in addition to this line of sight between my telephone and the cellular radio tower, there's going to be some buildings, and there's going to be a wall, and one of them is going to reflect off that wall and come back. So what happens is, I have a direct path, and I have one copy of the signal arrives fast, because it's, like it's shortest route. Here there's another route, and that little route takes longer, and so the symbol arrives later, and it interferes with the symbol that, the next symbol that came along. So then I get overlaid impulses due to these multiple reflections. So completely another way that I get intersymbol interference. So I bring this up because this leads to the use of filters, linear equalizing filters, in these scenarios, quite common. Okay, so not just this example we've been giving, but also in others. So I did a little chart here, but here's a nice little drawing that shows what happens between a cellular and a cell tower and the client here, who is a mobile, who's going around in the car. And we call this multipath. And there are multiple reflections. The different reflections gives us ISI. And we call delay spread is being like the time interval over which I'm going to get, reflections. So there's the main path, and then there's a certain time, and I'm going to accumulate reflections. That's called delay spread. If the delay spread is greater than the time of a symbol, then I get this ISI due to reflections. So I like the multipath example because it makes it easier for us to sort of interpret what's going on in the time domain with this representation of the impulse response of the channel. Okay, so the impulse response for a multipath channel, very intuitive. I can write over here that it's basically a bunch of delta functions. I have a bunch of paths, and each one are delayed by a certain time. And so because of this time delay, I'm getting copies of exactly the same pulse, but repetitions separated by this amount. But of course, the signal is not completely unaltered when it's coming by these different paths. For instance, each one of the paths may hit a different reflector, and the reflector may have different characteristics. So some may absorb the signal a lot, others may reflect it with very little attenuation. The A here represents the attenuation exhibited on each one of the different paths, and it could be very different depending on what surface it's reflecting off of. Now, because the path lengths are different, that means I'm sending it on a carrier, right? A 2.4 gigahertz carrier or a 900 megahertz carrier. And there's some oscillator that's going around at 900 megahertz. And the one that went a little bit farther is going to have a different phase from the one that went directly. So this theta represents the phase difference introduced by this different length of channel. And so a multipath channel is described by an impulse response which has a time delay, has a phase offset, and has some specific attenuation. So this is the form of the impulse response, and we can see from this form of the impulse response that it will generate intersymbol interference because we're going to have overlapping bits. And because we have overlapping bits and intersymbol interference, we can get a bed error rate floor. Very bad for communications. So just think of the simplest example. Just two paths. Suppose that one path is like one symbol later than the other path. Okay, very simple conceptually. So the second route, it may be attenuated, probably is attenuated. But in this simple system, with one delay and the delay exactly one symbol, then essentially, if I was going to try and figure out what's going on in this channel, I would think about there would be 4 important bit patterns. The pattern 00, 01, 10, and 11. Because depending on what was the previous one, I will get a different reaction for the current bit based on what was happening before it. Because that is the memory of the channel, one symbol interval. Okay, so this is what a multipath channel is. That's the mathematical representation of it. We call this form of the impulse response a tapped delay line. So it's a model for the multipath channel. It's a method to characterize the impulse response of the channel. Here's another example. This one was with three impulses, separated each by one interval of a symbol. The second one is actually less attenuated than the first one. So these are probably all reflections. Generally, if there's a line of sight, it's the least attenuated. So here, this is probably reflected off of an absorbent material, reflected off of a very good reflector. But anyway, it's just one example. But if I were going to take this idea of the tap delay line, there's my graphic of it, and here's my mathematical equation for it. And finally, I could also have a block diagram for what's going on in a tap delay line model for a channel. And the idea is that I take a symbol in, I multiply it by this coordinate for the filter, and that represents both the amplitude and phase, complex coefficient. And of course then I put in a delay that shows me the next time interval, and that one gets multiplied by a different attenuation factor, etc. And so this is a block diagram that implements or illustrates what's going on in this mathematical equation. And this gives us the name, it's sort of tap delay line, because these are the taps and here are the delays. So this is a representation of it. And of course, if I wanted to know, here at the input is the signal at the transmitter, and here is the signal at the receiver after it has passed through this channel. And we know that the relationship input-output for the channel, which is a tap delay line, we could write this as the system. We have X as the input, Y is the output. And the system I can represent by H of t, which would be the impulse response. And from Fourier theory, I know that the output is just the input convolution with the impulse response. So what I do is I look over here, say, okay, I want to know what is the output after the channel, that C represents after the channel. And so I have to take my input convolution with H, but then I say, what is H? It's this. And of course, X of t convolution with delta of t minus tau would just be X of t minus tau. So that means that essentially at the output of my channel, I have this representation, which is exactly what we see inside of this tap delay line. So this is how we can get the tap delay line directly from this relationship for the representation of the impulse response. So we have this model for the multipath channel being a tap delay line. Now I want to come up with a linear equalizer which will combat this effect introduced by the tap delay line. And the filter that I am going to propose is actually another tapped delay line. So the exact structure that is introduced by the channel, I will use the same form at my receiver to try to undo what was done by the channel. So in this case, I have, again, coefficients of my filter, only now it's the filter at the receiver, and what my task is to find out what are these generally complex coefficients for this filter at the receiver in order to undo what is done by the channel. And we call this a transverse filter, this structure of filter. And what we're going to do is we're going to introduce a strategy that lets us choose these coefficients in order to achieve a certain behavior. And the behavior you're going to want to do is to force the component from intersymbol interference to be 0. And that's why we call this a zero forcing equalizer.